Sorry, say what? Okay. Right. So I'm going to talk about spanning trees with few branch vertices. This is joint work with my thesis advisor, Ron Gould. I finished my thesis just this past year, and this work is, we're still editing, but we are very much hoping to publish this soon. Okay, so spanning trees. So, as we know, every connected graph has one. So here we have a connected graph, and here we have a spanning tree. Okay. So, some terminology. In a tree, a vertex of degree 1 is called a leaf. A vertex of degree 3 or more is called a branch vertex. Now, one big reason to care about spanning trees is that Hamiltonian paths, which we all care a lot about, are a special kind of them. Now, they're special in a few different ways. Their max degree is only 2. They have only 2 leaves, and they have no branch vertices. And so, if we have a graph and we would like to find a Hamiltonian path but we can't, then maybe we can find a spanning tree that sort of comes close to that goal. And close can mean a few different things here. It can mean low maximum degree, it can mean few leaves, or it can mean few branch vertices, and that last one is what we focused on. So, if I say one spanning tree is better than another, I mean it has fewer branch vertices. So, with all this in mind, what conditions might lead to a good spanning tree? One thing to look at is independent sets. And the reason I've listed this as a kind of opposition is these two kinds of properties actually pull in opposite directions. So if you keep adding edges to a graph, you can find better and better spanning trees. On the other hand, if you keep removing edges, you can make larger and larger independent sets. And so because these two things are kind of opposed in this way, if you set the right parameters, you can ensure that one thing or the other has to exist. But there's more. If you're looking at different independent sets of the same size, you can look at their total degree, which is that you add up the degrees of all the vertices in your independent set. And the question is, can you make that, how small can you make the total degree? And so, if you keep removing edges, you can make that number smaller. So, elaborating on the previous thing, if you set the right parameters, you can either find a good spanning tree or a large independent set with a small total degree. And of course, if, like many Hamiltonian-related problems, being claw-free helps a lot. And so now we might ask, what are the best possible parameters? So, this is a theorem from a few years back of Matsuda, Ozeki, and Yamashita. Let K be a non-negative integer and let G be a connected claw-free graph. Then G contains either a spanning tree with at most K branch vertices or an independent set of 2K plus 3 vertices. And the same people in the same paper pose the following conjecture that says almost the same thing. As before, either the same spanning tree or an independent set of 2K plus 3 vertices with total degree at most at V of G minus 3. So I claim both of these are best possible. And I'm gonna, the same example will show you why for them both. So the example looks like this. The big circles you see are all cliques with M vertices each, and then you've got this row of triangles there. So first of all, this is connected and claw-free, like we said. Now, if you look at the triangle I've highlighted in red here, any spanning tree for this graph has to have. So the thing. There needs to be a part that shoots out the top of this triangle, another part that goes down and to the left, and another part that goes out to the right. And so therefore there has to, one of those 3 vertices in that triangle there has to be a branch point of that spanning tree. And so any spanning tree for this thing has to have a branch vertex somewhere in that triangle, and the same is true for all of these other triangles. And because there are k plus 1 of those, there you cannot find a spanning tree with only k branch vertices in this structure. Now, how does so that takes care of that. Now, what about independent sets? So first, let's count the total number of vertices in this thing. The red boxes each contain m vertices, and there are k plus 3 of them. The blue boxes each contain 2 vertices, and there are k of them. So the total order of this graph is the expression that you see there. Now, how big an independent set can we make? Well, each of the boxes, both red and blue, has a clique inside it. So if we make an independent set, we cannot have more than one vertex per box. And there are k plus 3 red boxes and k blue boxes, so the biggest independent set we can have is 2k plus 3, like what the theorem mentioned. And so now the thing you might ask is, well, if we take the biggest possible independent set, how small can the total degree be? So in order to keep this total degree as small as possible, we have to have a vertex from every box, assuming we can do that to begin with. So for the red boxes, we have to pick something out away from the triangles to keep the degree down at m minus 1. And then there are k plus 3 of those, so we get this expression here. As for the blue boxes, they're all the same. They've all got degree 3, so as long as we keep them not adjacent, that is going to add up to 3k. And so we do some algebra, and it turns out to be v of g minus 3, like what the conjecture said. Okay. Any questions so far?
Was that known when the conjecture was made already?
Yeah. The authors of that same paper gave this counterexample and specified that for both. Okay. So now I'm going to talk a little about some partial progress towards the conjecture in the sense of small values of k and how those were shown. So at the bottom of the screen here, I have a sort of related theorem which is about leaves instead of branch vertices, but it's going to turn out to be useful for the small cases. Now a direct corollary of this theorem is that if the theorem here is about leaves, not branch vertices, and if you plug k equals 0 into this theorem, you get the corollary that you see there on the bottom of the screen. Now, what's interesting here is a spanning tree with at most 2 leaves has to be a path. Therefore, it can't have any branch vertices. And if you plug k equals 0 into the conjecture at the top, you get the same statement at the bottom, and therefore this conjecture has to be true for k equals 0. I believe the authors of that derived the same conclusion from some other result. I don't recall which one. You can get it any number of ways, but that is. So that one is fairly automatic, and then the same authors showed it for k equals 1. And in the partway through my time at Emory, Dr. Gould and I showed it for k equals 2. And I'm going to spend a little bit of time here outlining how we did that. So, first of all, let G be a connected claw-free graph. So by contradiction, we're going to assume that neither of the things we're looking for is there. So there can't be a spanning tree with only 2 branch vertices, and there can't be an independent set of 7 with total degree v of g minus 3. So if we plug k equals 4 into the thing at the top, we find that the big independent set with small total degree can't be there, otherwise we'd be done, so there's got to be a spanning tree with at most 6 leaves. And so now is the part where we might have a whole bunch of spanning trees to choose from, and we've got to be clever about which one we choose. So, first things first, we're going to make sure there's as few branch vertices as possible. That's the thing we care about, so it makes sense we would put it first. Secondly, we're going to have as few leaves as possible. The third thing is a very specialized thing that I'll tell you in a minute, And the fourth thing is that the parts of our tree that are in between branch vertices should be as small as possible. So having more vertices out toward the dependent paths and fewer of them in between the branch points is going to be preferable. But that condition does get last priority after these other ones. Okay. So how many different structures could our tree possibly have? Okay. First possibility is that there are only 5 leaves. Now, they can't be less than 5 leaves because there had to be at least 3 branch vertices, and that forces 5 leaves. So the only way such a tree can look is this way. And by the way, these line segments that you see are not individual edges, they are paths. Keep that in mind. They could be arbitrarily long. But this, topologically speaking, this is the structure. Okay, so a couple of other possibilities here. Our tree could have 6 leaves, but still only 3 branch vertices. That would mean one of them would have to have degree 4, and so the one with degree 4 could be in the middle, or it could be out on the end. And that T3 condition I referenced earlier is that we pick the first type over the second type, if that's the choice we're making. Any questions about that so far? Okay. So the last couple cases are for there to be 4 branch vertices and therefore 6 leaves. There can't be more than 4, otherwise there would be more than 6, and we know there's got to be something with 6 of this. So one of them looks like this, and the other looks like this. And despite the appearance of it, the one on the bottom is actually the more symmetric of the two. That one in the center, it's the same all 3 directions, despite the appearance for compactness. Okay, so just for that first case, the one with only 5 leaves, I'm going to give an overview of how this argument would go. Okay, so here's that structure. First, we're going to choose an independent set, and we took this one. Now in order to show that it's independent, we need to check the possible things that could be adjacent. And so I'll just show one example of that. This one right here is, if this edge is part of the graph, then we can make a different spanning tree with one less branch vertex than before. So that's a contradiction. Okay, secondly, we're going to partition this tree into different parts. Here are some labels for all those parts. Each label, you go to a black vertex in one direction and a red one in the other, and so every vertex is in exactly one of the labeled things here. Okay, so we're going to consider just one part at a time. The example I'll show is M1. And certain sets of neighbors of the red guys need to be disjoint, and I'll kind of walk you through that. So we've labeled all of the vertices in our independent set, and here's 2 sets related to B1 and B2, and then here's 4 others related to all the leaves that are not L1. Now I claim that those 6 sets are all disjoint. So just to give you one example of that, let's suppose that 2 of them contain this blue vertex right here, and let's suppose that it's L3 and L4 that are both adjacent to that. Well, if you look at this vertex above here, because this graph is claw-free, we can't have a claw like this. And right now it looks like a claw, so for it to not be a claw, there needs to be some other edge between some pair of those. Now, previously we would have established that L3 and L4 are not adjacent to each other, because they're both part of an independent set. So one of them's got to be adjacent to that other blue vertex there. And so I'll just show you the L4 example. We can make another spanning tree, and it looks like that, and one less branch point than before. The other case I didn't put in, but it's very similar. Okay. So, now there's one more set here. It's related to the neighbors of L1, but in this case we have to take the set and shift it by 1. So what I mean by that is, if we take that vertex here, and it's a neighbor of L3, then the one just beyond it can't be a neighbor of L1. And so in this situation, we can make this tree right here. And so the minus means that you take the set and you move one step back toward L1. And so a very similar kind of argument would show that all 7 of the sets I've listed at the bottom are in fact pairwise disjoint. So we have all those sets. They're all pairwise disjoint and they're all part of M1. So so first of all, this is the number of this is the neighbor. The total number of neighbors of everything in X that land on the M1 path. And okay, so first we're going to split it into the leaves and the branch points. Then we're going to separate off L1 from the others. And now we're going to take that set and shift it, like I mentioned. And it turns, and shifting doesn't change the size of the set, it only just moves the set. And so now we have 7 pairwise disjoint sets. They're all part of M1, and so the total cardinality of that can't be any larger than M1. Okay, and so we do a very similar thing with all these other paths. So first of all, first thing to notice, M4, M2, and M5 all work just like M1, just by symmetry. So those kind of take care of themselves. As for M3, we're going to label this vertex in the middle here and the one right above it. And it turns out we can even do slightly better here. We can do a very similar argument, except that we can do better in the sense of excluding that blue vertex there that I'm calling Z minus. Now, similarly, the Q1 and Q2, we can take these 2 green ones on either side of there, and we can exclude them as well. And so now we're going to get to bounding the total degree. Now, the left side of these inequalities, these all add up to the total degree of our independent set, just because every part of the graph where these, every part of the graph that they could possibly have an edge to is accounted for some in one of those things. And so the left-hand side is the total degree of the graph, and as the total degree of the independent set. And the right-hand side is the order of the graph minus 3, because we've counted every part of the graph exactly once, except for those 3 that are in green that we left out. Okay, so that is how we show the total degree in that first case. I won't go through that for the second and third cases, except to just briefly show you which independent set we chose. It was these, and then here. So okay, here we added a 5th condition to minimize the length of that path in the middle there. So here we picked this one, and then this one. So that's all I've got as to the k equals 2 case. Now I'm going to move into talking about the general case and just a very brief overview of the new ideas that were needed for it. Okay, so here again is the conjecture from before, and the same conjecture, we think, is now a theorem. We're still editing, like I said, but I'll just do a very brief overview of how we're doing this. So the beginning is pretty similar. Let G be a connected quadrilateral graph. Assume there's neither the spanning tree nor the independent set, as before. And we're going to choose a spanning tree with the fewest possible branch vertices. And there's also other conditions there that I won't bother listing, because some of them are pretty intricate. Like, we're having to weave together like the distance between the branch points with the number of leaves and the degrees of them in some ways that I don't have time to get into. But one big question you might be having is, how do we keep the total degree down like we want to? So we chose a spanning tree with not many branch vertices, but to keep the degree down, we've got to get the disjoint sets just right, and it might not, because we had that shift in the one case, it might not be clear what direction the shift has to go. So we can rule out some combinations of neighbor sets, but like I was saying, no, getting the shift just right in every case is quite tricky. So our methods from before do not generalize. But the way we're handling this is to look at the edges of a spanning tree. And conveniently, there are exactly order of the graph minus 1 edges in any spanning tree. Okay, so I've coined a couple new terms. The first one is oblique neighbors. And I'll explain what that means. This is a relationship between a vertex anywhere in the graph and an edge of the spanning tree. And so what it means is, so take this red edge that I've highlighted in red there in the middle. For a vertex somewhere to be an oblique neighbor of that red edge, then it has to be adjacent, not in the tree, just in the graph overall, to whatever vertex is on the far side of the red edge from the other vertex in question. So for W to be an oblique neighbor of the red edge, this blue edge that I've just put in here has to be part of the graph. Similarly for X, it has to be like that. But for Y, it has to be adjacent to the other side, because it's whichever one is farther from the other one you're looking at. And then Z similarly over here. I'm calling it oblique because it has to go to the far side. So, okay. One quick note, every spanning tree edge actually has both its incident vertices as oblique neighbors, because the one on one side is adjacent to the one on the other side in the tree and therefore also in the graph. So that one is just a sort of trivial case of this. And okay. And building on that, I've coined another term. I'm calling it pseudo adjacency. Two vertices are pseudo adjacent if any edge has them both as oblique neighbors. So for W and Z to both to be pseudo-adjacent using the red edge, both of these edges would have to exist. And in this case, we can make another spanning tree, and we have one less branch point than we did before. On the other hand, if they come from the same side, we can use a claw argument. And so either we have this blue edge here, in which case we can do something like that. Either that or either W or X needs to be joined to the left side of the red edge. And in that case, we can do something like this. And so you see how in most of these cases, it's not that hard to get the contradiction we need. Sometimes it's harder than usual, and that's why all those other conditions were needed that I don't have time to show you. But that just gives you a basic idea why these concepts are helpful. So first of all, the degree of a vertex in the overall graph is actually equal to the number of oblique neighbor edges that it has. And so the reason for that is that if you take any vertex in the graph and you look at all the edges coming out of it, every edge has to land somewhere else on the tree, and whatever spot it lands, there's got to be one edge of the tree that's pointing back toward where you started. There could be any number pointing away from it, but there can only be one pointing back towards it, and that's why this is a one-to-one relationship. So now, pseudo-independent set means that no two vertices in it are pseudo-adjacent. That's the other word that I coined, and it's sort of straightforward, except that pseudo-independent is actually stronger than independent because the other one is weaker. So how high is n minus 2k minus 3 the best you can do, or is it n minus 3 like our other results said, or is it somewhere in between? But one thing that I at least was surprised by is that number doesn't depend on t, it only depends on n and k. So new conjecture based on that. We know this conjecture will be sharp if it's true, but we don't know whether it is or not. And that's all I got. Any questions?
16 more slides. What's on here?
Okay.
270.
It's probably the graveyard of the
Okay,
slides.
I didn't mention this because I was short on time, but as I brought up pseudo adjacency, one thing you might have wondered about is there how is that any different from what I did in the k equals 2 case? And it wasn't different in the part that I showed you, but it was different in another part, and the other slides have an example of it being different. I might be out of time, but I'm happy to send my slides to you or anyone else.
Just
Yes.
a question. You mentioned about the link to Hamiltonian paths, right?
Yes.
Of course,
Hamiltonian paths are just a special case of this, yeah.
Yeah, with less branching trees, branching vertices. I'm just curious, because I haven't read literature. Because Hamiltonian paths are related to the traveling salesman problem, right?
Yes.
Yeah. So, and I mean, minimal spanning trees are the basis of most of the approximation algorithms like Vertices and so on and so forth. Is there any research done on spanning trees with few branching vertices and how well it approximates the TSP problem?
How well as in like how
well it approximates. I mean, Vertices does it to 1.5, right? If you have a guarantee that it has few branching vertices.
I guess I don't know for sure. I guess it seems. I mean, just whether there's a Hamiltonian path or not, that might still be hard to determine, even if you find something with only one branch point and only 3 leaves. The Hamiltonian question could still be made hard.
Yes.
I think.
Yeah. I'm not sure.
Yeah. I mean, this is a yes or no question. It's not a how many question.
Yeah. But if it's just approximation for the TSP.
Yeah. I mean. Well, I guess with it being a cost analysis thing, that would be different. I have not thought about that.
Sure, no worries.
Yep, you initially scared me with the 233 slides.
I'm more worried as a chair.
Is that really it?
I hope you found the diagrams helpful, because
Yes.
that's the main reason the numbers.
Yeah, I know.
Alright, any more questions? Okay, if not, let's thank all the speakers for this session. Alright, so we will proceed for lunch at the outside the LT. After that, the first talk will commence at the LT with the plenary session by today is 2V. Yeah, Professor Esjon.
And we'll be back on schedule.
Yeah, what time?
Okay.
Yeah.
Yes. We'll be back on schedule after that. Of course, lunch is very long.
Nine.
It did feel like a